All right, so yesterday when we ended class in this scenario. And we talked about how these two data points here that we added on in problem number 6 of the green packet, or in question 6 of the green packet, kind of debunked our exponential growth model. Because the growth slowed, and we said it's realistic that there's not going to continue to be exponential growth of Starbucks stores. Because there would be Starbucks stores eventually, if it continued to grow exponentially, the entire country would be a Starbucks store, or multiple Starbucks stores. And then the entire world would be Starbucks stores. So there's only a limited amount of space that we have in the world, right? And so if this continued to grow exponentially, every building would eventually become a Starbucks store. And then every open space. And then the oceans. And then the moon, and so on and so forth. It just would keep growing and growing and growing. Okay? So we said there's got to be a limit. It's got to cap somewhere. Because realistic, it's just not feasible. It's just not true. Okay? So we said that that is something called a logistic function. Okay? And a logistic function is a better fitting model for this data. Okay? The logistic model has an upper limit to growth. So basically, a logistic function, and we're going to develop one here momentarily, a logistic model starts out and it grows exponentially. But then there comes a point, and we call that point the point of inflection. So the point of inflection is somewhere right in about there. There comes a point when that then switches from an exponential growth and it levels itself out and it ends up reaching what's called the upper limit. Oops, I missed. Okay, so the upper limit would be somewhere up in there. Okay? All right? So my question to you is, based off of the data that you have in front of you, what do you think would be a realistic upper limit to the number of Starbucks stores that there are? Based on the data that you have in front of you, based on your knowledge, what do you think? What do you think is an upper limit based off of our scatter plot?
I guess I could logistically bridge around 7,500, 8,000.
Well, we already know that because we added those 2 on at the bottom, so we're already up over 8,000. Okay? So we're already up above 8337. 10,000 sound like a good number? Yeah? Okay. So let's go with an upper limit here of 10,000. Okay. Okay. I'll go with an upper limit of 10,000 for the day. And I'm cool with that. Okay. Is that truly the upper limit? I don't know. I mean, on this one, it's actually, I think I got it at, let's see, where is it at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like 11,250. Okay? Right? But I'm fine with 10,000. Okay? That's cool. All right? So, we're going to come back to that in a minute. Okay? But first, we're going to talk about what a logistic function actually truly is. Okay? Exponential growth, we talked about being unrestricted. Okay? It's going to grow forever. There's no limit. There's no upper bound to it. It will continue to increase at an ever-increasing rate. So the more stores you get, the more stores you're going to get the next year. Okay? And then it's going to go up by more stores after that. It's going to keep, that rate is always going to be increasing of how many new stores you get. Okay? Not many very realistic. We talked about that already. Okay? And there's many growth situations where there is a limit to the growth. Okay? If you go out and you plant a tree, okay, or you planted maybe in 4th grade, do you guys get trees? I think it was in 4th grade you got trees for Arbor Day. Okay? And you might have planted that tree. Well, that tree grew. Okay? Right? And it grew and it grew and it grew and it grew. That tree eventually is going to stop growing. Okay? It's not going to grow forever and ever and ever. Okay? It may be planted for a long time, and I hope it is planted for a long time, but it needs to have a limit to the growth. Okay? Right? Because it's not going to all of a sudden reach the moon. You know, in 15 years, that tree's not going to be all the way out to the moon, and then all the way out beyond. Okay? It's going to have a limit to its growth. Okay? Population of a city growing is another logistic model case. Okay? The city of Wausau could not continue to grow at an exponential rate because there's only a limited amount of space that the city of Wausau can occupy. Okay? If it would grow exponentially, soon the city of Wausau would take over all of Marathon County. Then it would take over all of the state of Wisconsin. Then it would take over all of the upper Midwest. Then it would take over all of the United States. Then it would take over all of Canada and Mexico. Then it would take over, you know what I mean? It would just continue to grow, and all of a sudden the city of Wausau now is the entire world. Then it's the entire universe. Then it's, you know, and so on and so forth. Because there's no limit. There's got to be a limit. Okay? So, logistic functions actually have two horizontal asymptotes. They have a lower horizontal asymptote, which we call the lower bound. Typically, that is 0. Okay? Because we're talking about a real-life model situation of it. I can't have negative 15 Starbucks stores. Okay? My tree can't be negative 3 feet above the ground. Okay? Or in height. The height of my tree can't be negative 3 feet. Okay? But I do have, now let me see if I can actually move this down here a little bit. But I do have an upper bound. Okay? And that is my limit to growth. Okay? The upper limit, we'll call it a couple of different names here today. Okay? We'll call it C as one name. We'll call it upper bound. We'll call it limit to growth. We'll call it limit to certain things. Okay? But that's that upper, that's that maximum value that that particular item can grow to. Okay? Logistic functions take one of two forms. We are going to focus in on the left form today, but we could also make a logistic function in the right form with base E. Okay? But we're going to make it, today we're going to focus in on just the left form. Okay? So my numerator of the fraction is my limit to growth. Okay?
So that's the numerator, is that upper bound, that upper limit, that C value is my numerator. Okay? My denominator is a exponential growth, I shouldn't say it, excuse me, is an exponential decay function. And it needs to be an exponential decay function because mathematical sense, number sense, if you will, tells me that if I have a number, a fraction, let's say, 10 over 5. Well, what is 10 over 5? It's 2. But if this number grows, this denominator gets bigger, okay, what happens to my value? It gets smaller. It's inverted. Okay? So this denominator here needs to actually get smaller in order for my function to grow. Okay? So that's why this value, or this part here, needs to be a decay function. So because it needs to be a decay function, b has to be between 0 and 1. This function over here needs to be a decay function. Oops, not a decay. Learn how to spell, Linsmeyer. I mean, my God, you're a ma'am. Okay, so that one needs to be a decay. So this negative sign has to be right there because that makes it an exponential decay. All right, so we have to have a negative k there. B has to be between 0 and 1. What? Who needs new friends? Oh yeah, the dude from yesterday? Yeah. Yeah. Huh? If b is bigger than 1, or if k is positive over on the other side, then it's called a logistic decay, and we're not going to get into that because there's no need to. Because a logistic decay function would look like this. Right? And we wouldn't need any of that because we would just use this part and it just becomes an exponential decay. That part is just your exponential decay part and we wouldn't need to be a logistic decay with it. Okay? All right? So we don't need, that's why we want b to be between 0 and 1 and we need that one to be negative. Those are locked in. Okay? Now, let's come up with a logistic function, that satisfies those conditions. Okay? So the first condition says that our initial value is 12. Yes, I gotta do the whole thing. Oops. Our initial value is 12. I just want to give a little more space here. Okay. Our limit to growth is 60, and the logistic function also passes through that point. Okay. So I want to make a function f of x equals c over 1 plus ab to the x power. That's the one that I want to go with. Okay. Do I have, so I need to find A, B, and C. Do I have either A, B, or C from my data, from my conditions, if you will? What do you got, Ben? A is 12. Do we agree that A is 12? We got some yeses, we got some no's, and we got some I don't know. Okay? I do not agree. A is not 12. So what is C? 60? Do we agree that C is 60? Yes? Okay. I get 100% response on that one, so I'm going to go with C being 60. Okay? All right? Okay? Now, I want to, because in exponential functions, that initial value, that was our A value, but we're not in exponential functions. So, here's how we get around that. So far, based off of my C, f of x is now that. Agree? Okay, I filled in my C because we 100% agreed that C was 60. Okay, so now let's use my initial value here. Let's use that point, 0, 12. Let's use that point and let's plug that point into our logistic function. So what am I going to replace? If I use the point 0, 12, how can I plug that into this function? Dylan?
F of x would become 12 and then x would become 0.
Okay, because this is a standard point x comma y, or x comma f of x. So 12 would equal 60 over 1 plus ab to the 0 power. Mathematically, b to the 0 power. Anything to the 0 power is 1. So really, that now becomes 12 equals 60 over 1 plus a. I need to solve that one for what? A. How am I going to solve it for A? Okay, so then we go 12 times 1 plus A equals 60. Then, so 1 plus A is 5. Then we subtract the 1, so A is 4. Would we agree that A is 4? Yeah, I'd agree that A is now 4. So now my logistic function can be written as f of x equals 60 divided by 1 plus 4 times b to the x power. Okay. Now what can I use? I've used 2 of the 3, and I still got to find b yet, right? So now what can I use? I can use my other point. So I'm going to use this point now to find b. Okay? How am I going to use that one? What? F of x is 24. 60 is 60. 1 is 1, plus is plus, 4 is 4, b to the first power. So really that's just 1 plus 4b down there, right? Okay, how do I solve for b? Multiply both sides by 1 plus 4b. Then what? Divide by 24. 60 divided by 24 is 2.5 or 5 halves. Then what? Subtract 1. Divide by 4 is the same as multiplying by 1/4. So b here is 3/8. So my logistic function then is f of x equals 60 divided by 1 plus 4 times 3/8 to the x power. Is that a logistic growth function? Why? What makes it be a logistic growth function? The b is between 0 and 1. Yep. So that one's going to grow logistically. Okay. What?
What if it's below 0?
It can't be. No. Yeah. Because you're always going to have positive numbers. It could be a bigger than 1 though, and then you did something wrong. Okay? Alright? What I'd like you to do now is I would like you to come up with a logistic function that satisfies the growth of this tree that I planted 5 years ago. Initial height of the tree is that, so we've got a C value here as our limit to growth. Do we agree that 30 is our limit to growth? Okay. So our function is going to start out, f of x is going to equal 1 plus a times b to the x, and it's going to be 30 on top. Concur? So far so good. Okay, so let's use our initial value as 0, 5. So that's going to be 5 equals 30 over 1 plus a b to the 0. So really that's just 1 plus a on the bottom there, right? Okay. So 5 times 1 plus a is going to equal 30. So 1 plus a is going to equal 6. So I get 5 as an a value. Concur? Okay. So actually it worked out that our initial value was also our a value. And that was purely luck. Okay. We can't say that that's going to happen all the time because we just did one where it didn't happen that way. Okay. Then, so now we can say that our function f of x is equal to 1 plus, so then it's going to be 5b to the x down there and 30 up there. Yes? And I'm going to use the point 3, 15. Now, so that's going to tell me that 15 is going to equal 30 over 1 plus 5b cubed. Concur? Okay. All right. So that's going to be 15 times 1 plus 5b cubed is equal to 30. So that's going to be 1 plus 5b cubed is 2. 5b cubed is going to be 1. B cubed is going to be 1/5. So b is going to be the third root of 1/5, or approximately, here's my papers, I think it's 0.58480. Because then it goes on to like 3 and 1 or 9. Yeah. Forgot the numbers. I just said them, but I forgot them. Yep. Okay. So our logistic function here would be f of x equals 30 over 1 plus 5 times 0.58480 to the x power. It is 9:41 a.m. Okay. Does your watch just normally randomly tell you what time it is? Well, you know, it happens. Okay? Alright? So now, what I'd like to do is, now I'd like to go back to this scenario, and I'd like to find a logistic function for this particular problem. So, let's talk about that Starbucks thing. We said that our limit to growth was 10,000 stores, correct? We'd said that at the beginning of class. Do we have an initial value on the Starbucks, or a t equal, or a, when our time was 0 value? We had 33, so we went through the point 0, 33. Our initial value was 33. Okay. Then, yesterday, in the two classes that I had, they both picked 10, I think it was 1886. Is that right? Year 10? Yeah, they both picked that one. So let's pick that point again. Okay? Alright? So, from the start, our function, we'll call it L of x, is going to equal 10,000 over 1 plus ab to the x. Right? Then, let's use that and the point 0, 33. Now, these numbers are not going to be nice. I can tell you that right now, because 33 doesn't evenly divide into 10,000. Okay? So, 33 is going to equal 10,000 divided by 1 plus a down there, right? Because really it's ab to the 0 power. We'll just call it 1 plus a. Oops. Times 1 plus a equals 10,000. So 1 plus a is going to be 10,000 divided by 33. So a is going to be that minus 1. Okay? So I'm going to go to my calculator. First I'm going to close out on that. And then I'm going to go here. I'm going to go there. And I'm going to say 10,000 divided by whoa, tap the brakes. Divided by 33. Come on. Minus 1. And that I'm going to store as my A value. Okay? So I'm going to store that as my A value. Okay? So that's in my calculator. Okay? So now my function L of x can become 10,000 over 1 minus A times b to the x power. And A is already in my calculator. What's up? Minus 1?
1 minus A times on the left.
Oh, sorry, because I forgot to put the other part of the plus in there. I get all jazzed up. Okay. Then we said we were going to utilize the point 10, 1886, right? So 1886 is going to equal 10,000 over 1 plus AB to the 10th power. So 1886 times 1 plus AB to the 10th power equals 10,000. 1 plus AB to the 10th power is going to equal 10,000 divided by 1886. AB to the 10th power is going to equal 10,000 over 1886 minus 1. Then I'm going to divide that by A. Then I'm going to take the 10th root of that. So it gets kind of nasty. Okay? Alright, so here we go. I want the 10th root of, now I've got a fraction, and in that fraction I've got a fraction, and that fraction is 10,000 divided by 1886. Then I've got to subtract 1 from it, and I've got to divide that by A. Gets me that. Okay? Yes, ma'am.
Okay, mine says non-real calculation.
Do what?
Put that in my calculator. That looks just like yours.
Do you have it? Did you store your A value in? I don't know. That I want to store as my B, which for you, you can store it as B, that's fine. I'm going to store it as G, oops, not double G, just G on my calculator, because I've already got a B stored in there, and I want to keep it on there to show you guys a little bit later on. So, okay, so that's going to be there. Okay, so my function, let's go, what is A approximately? A approximately is 302, we'll say. Okay, so my logistic function then is L of x is equal to 10,000 divided by 1 plus 302, oops, wrong one, this one, 0.03 times, what was my B value, 0.6537, 0.6537 to the x power. 6537. Yeah, I rounded it to 4. Okay, it's going to be exact on my calculator, but okay. So that's my logistic function. Helps to store stuff in it. Let's actually make it look prettier. There we go. And bad 10,000. Oh yeah, much nicer there. Okay? Now, let's put that on our graph. Okay? So, I'm going to have to go over here now. And I am going to go tab. And I am going to have a fraction. And the numerator is going to be 10,000. And the denominator is going to be 1 plus a, because that's my a, times, and I went g, and you guys went b, I went g, to the x power. Okay. And that fits our data a little bit more, yes? Okay. Now, if we would have jumped out maybe another point, another data point, okay, it might have fit the tail end a little bit better. Okay, it's just something you got to play around with, okay, and finding the right ones. Okay. So there, capture there. So now let's tap the brakes here. Question number 9 states, use the logistic function to estimate when the number of Starbuckses will reach 11,000. We did this yesterday with our exponential. Now with our logistic, when will it reach 11,000 stores? Why not? So if our upper limit is 10,000, can we ever reach 11,000? No. Okay, that's not possible on this current model. If we would have tweaked that upper number to something bigger than 11,000, yes, then it would work. Okay? Okay? We need to find L of 10. Well, we used that 10th point, so it's going to be the same. But if I were to just quickly show you how to do that, because we're dealing with f sub 2 here, I would type in f2 of 10, and I would get the number that we had. We used that one. Okay? And then the next one was, what if we wanted to find the, in year 2015, well, that would be f2 of 27, and there would be almost 10,000 stores in 2015. Okay? Have a great, grand, and wonderful day.